All right. Hello, chemistry class. This is Coach Jeans, and today we're going to talk about the combined gas laws. And so, if you remember in the last video, we talked about Boyle's law, Charles' law, and Gay-Lussac's law. Now, remember, Boyle's law relates pressure and volume. And so, it basically says that pressure goes up, volume goes down. It's inversely proportional. Okay. Charles's law relates volume and temperature. It says that if temperature goes up, volume goes up and vice versa. So it's directly proportional. Gay-Lussac's law deals with pressure and temperature. And so if temperature goes up, pressure goes up, another direct proportional. Now, what we can do though is we can take these laws and we can combine them all together. And this is what we call the combined gas law. Now, if you remember the combined gas law, then you don't have to remember the others. Basically, all you have to do is remember this one equation, P1 times V1 over T1 equals P2 times V2 over T2. And then if you're solving one of these gas law problems, and let's suppose that maybe the temperature is constant, well, then you can cancel temperature on both sides of the equation, which gives you what? P1 V1 equals P2 V2. That's Boyle's law. Well, what happens if pressure is constant? Well, you cancel P1 and P2 because they're the same, and so they would cancel out, and then you end up with Charles's law. And yep, you probably guessed it. If you cancel out volume, if volume doesn't change, then you end up with Gay-Lussac's law. But the question is, what happens though when two conditions change? For example, what happens when both pressure and temperature changes? What's going to happen to the volume? Or what happens when both pressure and volume changes? What happens to the temperature? That's where combined gas law can be a little bit different and a little bit unique here. So you'll want to get your calculator out, have your notebook open, and jot this equation down. If you don't have those things, pause the video, go get those things, and be ready to go. All right, this is example problem. So pause your video here, copy down this example problem, and then we're going to solve this one. Okay, so it says you have a 2.3 liter balloon at 15 degrees Celsius and 570 millimeters of mercury is taken to the top of a mountain where the temperature is colder. It's minus 15 degrees Celsius and the pressure is lower, 425 millimeters of mercury. What is the final volume of the balloon? So two things are going on here. We have a change in temperature and we have a change in pressure. So we know that if temperature goes down, volume typically goes down because Charles's law. We know then, though, that if pressure is lowered, then volume is increased according to Boyle's law. So we need to employ the combined gas law here to solve this problem. All right, so let's switch over here and let's solve this problem together. All right, so first of all, write down what's given to you in the problem. You have volume 1 is equal to what? 2.30 liters. Okay. Then it also gives you your pressure. Your pressure 1 is equal to 570 millimeters of mercury. And it says that our temperature is 15 degrees Celsius. Now, again, remember when you write down your temperature, always convert that to kelvins. And we do that by adding 273 to it. So that gives you 288 K, 288 kelvins. Now, what is the new pressure? Well, it tells you that you go to the top of the mountain and you have a new temperature, okay, of negative 15 degrees Celsius. So again, convert that over, and so that'll give you 258 K. 258 K. All right, our new pressure at the top of the mountain is 425 millimeters of mercury. 425 millimeters of mercury. The question says then, what is going to be the new volume? Okay, how big is the balloon going to be? What's the new volume? So we have our equation. We have P1 V1 over T1 equals to P2 V2 over T2. All right, so we're going to plug in our variables here. All right, so we have our P1, 570. We have our V1, which is 2.30, divided by 288 is equal to our P2, 425, times what? V2, we don't know what V2 is, over our temperature, 258 K. So we're going to solve for V2. How are we going to do that? Well, we can use cross multiplication. So we're going to bring the 258 over here to the top, and we're going to bring the 425 over here, and we're just going to flip everything. So what we end up with is V2 is equal to 258 times 570 times 2.30 divided by 425 divided by 288. All right. So now we want to take out our calculator. Now, when you put this in the calculator, you're going to multiply the top and you're going to divide by what's on the bottom. Now, I know some students say, well, don't you need to multiply the bottom first? Well, you could do it that way, but to simplify it, if you just multiply the numbers on top and then hit divided by 425 divided by 288, that will give you the correct solution. So in your calculator, plug in 258 times 570 times 2.3, and then hit divided by 425, and then divided by 288. And you should come up with an answer of what? Go ahead and plug that in. 2.76 when you round it. All right? And so your volume is 2.76. And what is going to be the unit? Well, since our volume started out with liters, then our V2 is also going to be into liters. And so there's my final answer, 2.76. All right. All right, let's go to the next problem then. All right, example number 2. Pause the video here, copy down this example, and then we will solve this one. Okay, example number 2 says a sealed metal container, 250 milliliters, at 1 atmosphere and 25 degrees Celsius is placed in a furnace that is 500 degrees Celsius. What will be the final pressure? 500 degrees Celsius, that may not sound like it's too hot, but remember in Fahrenheit, if you just double it and add 30, so that gives you over 1,000 degrees Fahrenheit on your furnace, okay? So pretty hot, pretty hot. And remember, this is a sealed container. And so the pressure is going to do what? Going to get higher and higher and higher until the can explodes. Never do that with a sealed can like an aerosol can, a paint can, or hairspray can, or anything like that. Never stick that in a fire. It plainly says do not incinerate. These things can be dangerous. They can explode like a bomb and hurt people. And so please do not do that. Okay, let's go over to our paper and we will solve this one. Example number 2. All right, so what are some things that we know here? Well, here we go. Example number 2. So we know, get this thing straight, we know that our volume, V1, is 250.0 milliliters. We know that our P1 is 1.0 ATMs, or atmospheres. We know that our T1 is 25 degrees Celsius. Let's go ahead and add 273 to that. So we get what? 298 kelvins, okay? 298 K. Now it's placed into a furnace, and so our T2 is going to be 500 degrees Celsius. So let's add our 273 to that, and we'll get 773 kelvins, all right? Now, the question is, what is the final pressure, P2? Now, what do we have here is we've got a sealed container. So if this container is a sealed container, right, what is going to be its final volume, assuming it does not explode? Well, the final volume is going to be equal to the initial volume. So V1 and V2 are equal. They're both equal to 250 milliliters. So we have our equation. We have P1 V1 over T1 equals to P2 V2 over T2. But since volume is held constant, then we can cancel it out on both sides of the equation because they're the same. And so that would end up canceling each other out when you do the math. So you can cancel it out right there. And so now we end up with P1 over T1 equals P2 over T2. Which law is that? Yep, that's exactly right. That's Gay-Lussac's law. So you see, you can use the combined gas law to solve any of these problems. You don't have to remember all the different equations. So let's go ahead and let's solve this one. So we're going to have 1.0 over our 298 is equal to, our P2 is our unknown over 773. Okay, so we're going to do our cross multiplication here, and we're going to say P2 is going to be equal to 773 times 1.0 over 298. So in your calculator, you're just going to punch in 773 divided by 298 because times 1 doesn't change anything. So 773 divided by 298 gives you what? That's exactly right, 259. And then this is pressure. So the unit for pressure that we started with was atmospheres. So we're going to have atmospheres as our final pressures. All right, hope that one makes sense. So let's go on to our next one, number 3, all right? Okay, let's take a look at number 3. You want to jot this down in your notebook and pause the video, and then we'll come back and solve it. All right, it says a 3.3 liter sample of nitrogen at 0.81 atmospheres and 22 degrees Celsius is compressed to a volume of 1.5 liters and a pressure of 2.5 atmospheres. What is the final temperature of the nitrogen? All right, let's take a look at this one. Solve it on paper here. Okay, so what do we have? Well, first of all, we're told the volume, so we know what V1 is. It's 3.3 liters. We know that it is at a pressure of 0.81 atmosphere, so that's our P1, and we know the temperature, so our T1 is 22 degrees Celsius, and so we're going to add 273, so that gives us 295 Kelvin. And then we said that it's compressed to a new volume, so our V2, 1.5 liters, and the pressure is 2.5 atmospheres, so our P2, 2.5 atmospheres. And the problem says, what is the final temperature? So we're trying to find T2. All right, so we have some givens. We have our unknown. We'll write down our equation, P1, V1 over T1 equals P2, V2 over T2. We're then going to plug in our variables just like we've done before, our given. So 0.81 times 3.3 divided by 295, make sure you're using the Kelvin, times 2.5 times 1.5 over T2. Okay, so now we need to isolate T2. Now T2 is on the bottom here, so when you cross multiply, you want to bring it up to the top. So I'm going to do this in 2 steps just so that you can see it and make sure you understand the algebra, okay? So the T2 is going to come over here to the top, and the 295 is going to come to this side to the top. So I'm going to rewrite it as T2 times 0.81 times 3.3 is equal to 295 times 2.5 times 1.5. Then I'm going to solve for T2. So I'm going to divide both sides by 0.81 and 3.3. So that's going to give me 295 times 2.5, that's a decimal, times 1.5, and the whole thing is going to be over 0.81, so 0, or over 3.3. Okay, so again on this one, you're going to multiply everything on the top, and then you're going to hit divided by 0.81, and then divided by 3.3 again. Now, if you're having any trouble with your math or anything like that, please get some help from your teacher in class, see your math teacher, see your chemistry teacher, and get a little bit of help with that. So you multiply the top, divide by each one on the bottom, and your T2 should come out to be about 414 kelvins. Okay, now that's in Kelvin temperature scale, which is fine. If this problem doesn't specifically ask you to put it into degrees Celsius, then you could leave it like that. But what if the problem asks you to do that, or if it's multiple choice and the choices are in degrees Celsius? Well, remember, to convert from Celsius to kelvins, we add what? Yeah, that's right. We add 273. So now we're going the opposite way. So instead of adding, what are we going to do? Yeah, we're going to subtract. So we're going to subtract 273 from that. And so when you punch that in your calculator, you get 141 degrees Celsius. So either one of these answers are correct. I'm okay with it in class if you put it as 414 on the worksheets or a quiz, unless I specifically ask for it. But again, if it's a multiple choice question or I ask you to put it in degrees Celsius, subtract 273, and this is also an answer. So either one of those answers are just fine with me. Okay, we're going to work some more examples in class and answer any questions that you have. So if you have anything, just make sure you bring it to class next time, and hope you have a good day.